All right, good afternoon, everybody. So we're starting chapter 6, which will be the latest chapter that will be on the next celebration, right? Yeah, let's see here. So we're talking about the normal distribution, which is on this chart. So everyone should have had one of these. Anyone not have one of these handouts? You need one, right? All right, so this thing's important, so don't lose it. It's also on the Canvas page. This is also table A2 in your online textbook. So if you go to the appendices and go to MyLab Stat, go to the appendices, right? You can find this as table A2. But this table is the standard normal distribution, right? So this is what we're going to do today. And then this will be part of what we do on Monday. Right? So my stuff is kind of important. Let's talk about it. So the normal distribution, right? Remember before the binomial distribution, right? You had a set of, right? Like Drippy shooting 5 free throws. He either makes 0, 1, 2, 3, 4, 5, 6. That's discrete, right? You have to equal exactly, there are exactly 6 possibilities, right? So each of those probabilities adds up to 1, right? When you add them all together. Now, the probability that an individual is of some height is also 1, right? But a person could be, you might say, well, there's a certain number of heights you can be, right? You could be 5'4", 5'5", 5'6", right? But actually, they're infinitely many, right? Because not everyone who says that they're 5'5", right? If I stood them end to end, is exactly the same height, right? Because height is a continuous distribution, right? So we're going to think about how do we look at continuous probability distributions, which the normal probability distribution is an example of. You're going to be able to think of that, conceptualize it, right, as area, right, under the curve of a continuous distribution, right? The distribution we're really going to talk about is the normal distribution. You learned how to calculate a z-score, I think, in chapter 2, right? So we're going to talk about what is a z-score in the terms of a normal distribution. And then we will use that to find probability. So we'll go z-score to probability, and then probability to z-score. And then you're going to be able to do these things both using technology, your graphing calculator. There's probably some way to do it on Excel. I'm not familiar with it though. And with this table, right? You might say, why do we need this table? This seems a little old school. It is, but you can put your hand on it. You can see the patterns and the values. I find that while the tables might be a little too old, might be old school, right? It strengthens students' understanding in a way that technology doesn't. So I'm fine after this class if you use the technology all the time instead of the table. But trust me, this table will help you get a feel for what's going on, right? Because you see the inner workings, right? It doesn't happen behind a magical computer screen. So what is the standard normal distribution, right? The normal distribution is a continuous probability distribution, right? And they represent things like height, rainfall, temperature. Those can all be represented by a continuous probability distribution. Which of the most common is the normal, right? Earlier, I shouldn't say either, earlier, we only used discrete distributions. Gotta stop. Now, here are 3 properties, right, of the, so notice there are 2 words here, standard and normal. Actually, it's kind of funny. Those are synonyms in everyday language, right? But these 2 things mean something very different here, right? So let me give you some 3 properties. Some of them have to do with the fact that we're talking about a normal distribution. Some of them come from the word standard, right? Let me start with one. So we already know that the normal distribution, right, is bell-shaped, right? Normal, we've told you, right, means I'm not great at symmetric, right? Highest in the middle, lowest on the edges, right? So we know that that's normal shaped, but normal is a specific kind of distribution that has that, right? So this comes from normal, the word normal in here, in that word. These two come from the word standard. So the standard distribution, right? A normal distribution is, right? For example, height of men in the United States is roughly a normal distribution, but it's not a standard normal distribution because the mean height is obviously not 0, right? And notice there's something, there's just a reason why we like this standard normal distribution. Is other normal distributions can be transformed to it, and it's the most convenient one. Because let's think about it. So we learned the formula from before. What is the formula for Z? The Z-score? You all calculated on your most recent large celebration. So it is, anyone remember? It's the number of standard deviations you are away from the mean. You remember that? So how would I calculate that? Well, I have my value. I want to see how far away it is from the mean. So when I want to see how far two numbers are apart, I subtract, right? And I want to figure out that distance, how many standard deviations fit inside of it. So if I want to figure out how many feet fit in a yard, right, in a certain number of yards, I want to divide by the size of my ruler, right, which is, does everyone remember this formula now that you're seeing it? Notice, in this case, the mean is equal to 0. The standard deviation is 1. So this is called the standard distribution in that the values associated are in fact your z-scores and your x's are the same thing, right? So that is very convenient, right? We don't have to translate to z-scores. Every value is a z-score. So that's why we want the normal distribution, the standard normal distribution. Since there are many distributions, right? Each normal distribution, right? Men's height in the United States, women's height in the United States, child's ear size at birth, right? They're all normally distributed. Each of them would require its own table. That wouldn't be very convenient. Luckily, we'll find a way to convert to a standard table probably tomorrow, right? But we're going to just focus on the standard normal distribution today. And the normal distribution has this particular curve, right? And we find out that areas, right, correspond to various regions underneath that curve. Right now, this is not an algebra class, but you guys have all learned how to graph certain types of curves, right? Y equals x, that's a straight line, right? Y equals x squared, that's a parabola that looks like this, right? And now, since I told you this is what the normal curve looks like, right? Maybe your friend draws one that looks like that, and you say like, hey, I'll pretend that's symmetric for a second. That's bell-shaped, right? But it doesn't quite look like this bell, right? So how do I tell them which one exactly is the normal curve? Well, we specify curves with equations. This right here is the equation for a distribution, right? Given a standard deviation and a mean, right? The mean is 0 for the standard curve. Standard deviation is 1. So if that's the case, we have E, you can just flip these out. Notice x minus 0 over 1 is the same thing, everybody, as, you're killing me here. X minus 0 is the same thing as, and x over 1 is the same thing as. So this becomes a little bit simpler, right? You put this in the y equals button of your calculator, you will get the bell curve, right? Now, you might not like that. Some of you may have forgotten what E is, or it's possible some of you never learned it. That's okay. Because while this is the equation that gives you the height of the bell curve at any point, we're more interested in areas under it. And, right, those of you who are intimidated by how this thing looks, don't worry too much. We won't actually use this equation really for anything in this class itself. But why am I teaching it to you then? To emphasize this point, that the bell curve, the normal distribution, is one specific curve, right? The standard normal distribution is a specific curve that can be graphed. So it has a specific equation. Y equals e to the negative 1/2 x squared divided by the square root of 2 pi. You don't have to graph it. You don't have to know why that's the equation. Just the idea is that there is a single standard bell curve, right? And since there's just one, there's an equation that goes with it. Again, this is what it looks like. Okay, now, you can see this equation, a bit messy, right? This shape, a bit messy too, right? We want to calculate areas underneath this curve and conceptualize them as probabilities and stuff like that, right? And this is because it's the most interesting and one of the few continuous distributions that's worth a damn, right? But it's somewhat complicated, right? So to get the idea of what some of the things are that we might want to do with this curve, it might be easier for us to find a curve that has a simpler shape to give us some ideas, right? So this next distribution I'm going to give you in itself is pretty unimportant, but it's going to help us develop ideas that we can then use for the normal distribution. Perhaps your friends who are in the other statistics class, maybe they don't do this at all. I just think it will help you understand it, right? So the uniform distribution, right? Remember when we did the relative frequency graph, a normal distribution had a flat top, right? It was just rectangular shaped. And that's exactly what's going on with a uniform distribution. So the uniform distribution is a continuous random variable, right? So random variable means variables, just like in discrete, instead of a variable that can take on like 6 or 7 specific values, right? It's a uniform distribution if your values have some range between them, right? So it's continuous. So for example, imagine 0 can be any number between 0 and 5, including non-integers, right? So x could be 0, x could be 5, x could be 4, x could be 4.5, 0.1, 0.2, 0.3, right? Now, this is very different, right, than the normal distribution. The normal distribution, it's random, right? But certain values are more likely than others, right? So imagine like height of a person, right, is a continuous normal distribution. But certain heights are much more likely than others. So in a uniform one, in a world where there are some minimum height and some maximum height, right? People are all taller than 4 feet tall and shorter than 7 feet tall. That's almost true in the real world, right? But within that height, you're just as equally to be 5'8", as you are to be 6'10". That's not the case, right? So a uniform distribution is something, right, that each value has the same, is as likely as any other value. So it has a rectangular shape. And the area underneath the graph of a continuous probability is equal to 1. Now, this fact right here is nothing special about the uniform distribution. This is every continuous distribution, right? I'm going to call this continuous probability distribution as C, P, D, not the medical condition, right? And it has to be equal to 1, right? Just like I was telling you, a discrete probability distribution, the probability of all the different outcomes have to add up to 1, right? So remember, we had one when we were playing a game, right? There are a certain number of outcomes. You either win no money, you win, it's like $9, $199, and $399. Some game I had like that, right? The probability of all the outcomes have to add up to 1 because those are the only 4 things, right? Just like that, the probability underneath the curve, since it's a continuous probability, have to add up to 1, right? If this doesn't, right, but if this represented the probability of being a particular height, right, the probability that a randomly selected person, everybody in this classroom, right, you all have a particular height that you actually are, right? So the probability that you have some height has to be 1. So if I added up the probability that a randomly selected person is 5 feet tall to 5'1", add them all together, the probability would be 1. Finally, right, there is a correspondence, right, between probability and area. This again is true for every distribution. It's not something special about the uniform distribution. But the uniform distribution is the easiest one to see this because a uniform distribution looks like, what shape is that there? Rectangle is right? When you were, I clearly don't have kids because I have no, and I clearly never taught elementary school because I have no idea when you learn the area of a rectangle in school, right? I second grade maybe. I don't know. First grade. I don't know. Guys have probably done it earlier. You're more likely to have younger siblings. I am totally. I'll know what age it is when my niece learns it, but she's now not even in kindergarten, so preschool, maybe smarter ones. I think that's identifying a rectangle. Maybe not. I don't. I really don't. I have no idea. I took adolescent development in teacher school, never childhood development. So let's just wait for this gentleman to be done mowing. Since in this case, right, we're having something where you're waiting for something, right? Let's talk about this. So you can find the area by using the formula height times width. Density curve. So again, as I already told you, right, we call this the density curve. You'll see why we called it that, right, in a second. The total area underneath the curve is always exactly 1 for every single every single continuous probability distribution. Just like the sum of all those values in the table for every discrete probability distribution add up to 1. Those are analogous facts. Here's the part that it's a little strange about. For a continuous distribution, the time I'm just ready to start up again, he's back, right? Everything, right? I tell people that I'm 6 feet tall. Anyone else in here 6 feet tall? Like, you tell people you're 6 feet tall? Okay, now when you've gone to the doctor, did they always measure you as 6, or have you ever measured under, or a little bit under, a little bit over? You've been measured as 6'2". Okay. So I tell people I'm 6 feet tall, right? But sometimes, and right, it pisses me off every time, but usually every time I go to the doctor now, right, since I'm a little tiny bit shorter than I was before, I measured just under 6 feet. So sometimes I measure it as 5'11 and a half, 5'11 and 3/4. Nobody is actually exactly 6 feet tall. Or, right, if you measure someone's height, that's as accurate as, right, maybe you go to 6 feet tall, but maybe if I use a more accurate ruler, use a laser thing, I'm 6 feet and 1/100th of an inch tall, right? And that's not really accurate either. Just imagine, right, the more accurate I have of a measuring tool I have, the more decimals will be in my height that I find, right? So in a continuous thing like height, the probability that any particular value is chosen is infinitely small, right? So really, we generally don't ask questions like, what's the probability that my continuous random variable is equal to some number? Instead, you want to ask, what's the probability that the variable falls in a particular range? So for example, right, if your tool can measure to the nearest inch, right, if you're measured at 6 feet tall, then we can conclude that your height is somewhere between 5'11 and a half and 6 1/2 inch, right? If your tool measures to the nearest 1/10 of an inch, right, then same thing, right? It's just 11.9, 0.1, right? So you can easily ask the probability that someone's height is in some particular small range around 6 feet, right? So because of that, there's a little bit of a trickiness, right? So we're waiting at the TSA line. Now I think, since considering what we just had happen, let's imagine that we're waiting for the landscaping folks to stop mowing the lawn so I can go back to teaching, right? So in that case, let's suppose, right, or in anything, whatever we're waiting for, it never takes more than 5 minutes, right? So this thing that we're waiting for, right, so it says it's uniformly distributed between 0 minutes and 5 minutes. What that means is it never takes more than 5 minutes, ever, right? It also means, right, and this is just common sense, but it could be randomly distributed around between 1 and 10, right? It never takes fewer than 0 minutes. That's obvious, but it could be something that's non-obvious, right? And it says it's uniformly distributed. So while each exact amount of time is infinitely small, they're all the same, right? So as I am as likely to be waiting for 1 minute, exactly 1 minute, as I am to be waiting for exactly 2 minutes, which is as equally likely as I am to be waiting exactly 4 minutes and 50 seconds and 1/130th of a second. You see what I'm saying here? Each waiting time equally likely. So we might ask you, right? So a uniform curve looks like this, right? And the function here, right, the fact that this line is flat shows you each time is equally likely, right? Maybe you can think about that. Well, I find my pen. This shouldn't be too hard. So the area in every probability distribution, the area is always equal to everybody. 1, in this case, the shape is A. And its area must be 1, right? So we know some people write length times width. I like to think of this as a height because it's a y position. So I'm going to write height times width. We know, since that you are waiting between 0 and 5 minutes, what's the width of this rectangle? Everybody, the width is 5, right? Because you can't be waiting fewer than 0. You can't be waiting more than 5. So it's pretty easy to find out, okay. So the width then, sorry, I don't using the height, I know the width. Height then would be 1/5 or 0.2. So that's the point of the curve, right? So we kind of have a piecewise function here. So P of x is equal to 0.2 if x, so we kind of have a piecewise function here. It's okay if you don't follow this notation perfectly, right? But this is just. So this is P of x, right? Because it's uniform, right? No time is more likely than the other time. Among the possible times, right? The probability is 0.2. Outside of 0 to 5, those times are impossible. So P of x is 0. Now, the 0.2 is confusing. What does that really represent? And the answer is, I don't really have a good answer for you on that. It represents the probability density. Because, again, the probability that you'd be waiting exactly 4 minutes is infinitely small, right? But the height has to be 0.2 so that the area adds up, and you can compare times, right? So if you have a non-uniform example, right, if P of 1 is bigger than P of 3, right, then P of 1 is more likely, but they're all infinitesimally likely because they're that. So that's one of the reasons why I said, like, here's the equation of the normal curve, but we're not going to use it much, is that the height of the curve doesn't really tell us much other than what values are more likely and what's less. We're more interested in area underneath the curve, right? So here's how you can use this, right? Remembering that area equals probability, right? Right, and we're talking about area underneath the curve between two vertical lines. Has anyone taken a calculus class where you've ever done integration? Anybody? Calculus? No? It's okay. We won't have to do that here, but you can, if you have, right, you can connect that concept. You're not going to have to use any calculus methods, I promise. Right, but wait time of at least 2 minutes. The wait time then is number of x. So least 2 minutes, that means x is what compared to 2? You say I've been waiting at least 2 minutes. You have been waiting more or less than 2? More, right? So we're trying the probability that x is more than 2. And because, all right, it has to be less than 5 because that's just the way. So that means we are finding the area in between the vertical line at x equals 2 and x equals 5. This is very easy to do so because this is a rectangle. It's length times height. So the length of this piece is 3. So really, it's so the probability that you'll be waiting between 2 minutes, more than 2 minutes, is 60%. And we got that by finding the area, right? And we could have probably figured that out informally, but I wanted to show you this idea, right? if you think about this, area is equal to probability. Each minute is just equally likely, right? Notice that that is true, right? Since it's a uniform distribution, I'm as equally likely to be waiting between 1 and 2 minutes as I am waiting between 4 and 5 minutes, right? Between 1 and 2 minutes, right, that would be 0.2, right? Between 4 and 5, 0.2, right? So notice that the intuition that we know about this matches area, right? So do we kind of get the main thing that you want to get out of this uniform distribution is that we are trying to find area, right? And that corresponds to the probability, right? So for example, if I wanted to find the probability that I wait between half a minute to 1 minute, that would correspond to roughly this area right here. That would have a width of 1 and a height of 0.2, so that would equal 0.2 or 20%. Uniform distribution. Not very interesting, right? So the main thing you're trying to get out is an intuition that of the uniform distribution is the intuition, right? And you can see that if that example didn't make as much sense for you, it's in the textbook, right? You can read through the same thing, right? We're giving you the intuition that for a continuous probability distribution, area means probability, right? It actually does in a discrete too. You could make a histogram bar for each bar, right, for each discrete probability. And then since all the discrete probabilities add up to 1, the area of all of those bars would also add up to 1, right? So we're going to do the same thing for the normal distribution, but it's not going to be easier because the rectangle is the easiest shape to find the area of, right? Here, we need to find the area under this much more complicated curve, right? Those of you who will take a calculus class or have, you'll find out that's the same thing as integration. But if you take a calculus class, you'll also find out this is a function that's very difficult to integrate. It's impossible to integrate algebraically. So there's not much of a point for us teaching you. If you ever take a calculus-based statistics class, which I don't imagine most of you ever would, right? You will learn the connection here. But we don't really need to worry about it, right? We just know that area underneath the curve corresponds to a probability, right? And since it's too difficult to calculate using some formula, there actually is no formula, perfect formula that allows you to calculate the area in a normal distribution. We will use approximations, which is this table and technology, right? So if you have a parent or a oh no, you guys, I keep forgetting, your parents are probably too young to have not had calculators in school. Your grandparents, my parent, yikes, I'm old now, right? Use this. Let's give some notation here, right? So whatever our variable is, it could be x or it could be z. Remember, for a standard distribution, right? X equals z, so we're just using z here, right? This is exactly what it sounds like. It doesn't matter what temperature it is outside, it's always warm in here, right? Between A and B, right, it's the probability that the z-score is between A and B, right? This is exactly what you notice here. Notice that I'm not using or equal to signs. I don't really care. That is the convention. You can use equal, greater than, or it doesn't matter, right? Because the probability that someone has a exact value for a height, a z-score, a weight, whether the probability that a building is an exact height, it's infinitely small, right? So the probability that a person is shorter than 6 feet tall is the same thing, right? The probability as if they're equal to, if they're 6 feet tall or less, right? Maybe you would say it's not quite the same as you would measure, right? The height that they'd be measured to, but it is in some abstract way if you could actually measure their exact height. You understand what I'm saying? The probability that they have any particular value is the same, right? So as far as we're concerned, the probability that z, right, we'll just say that these are the same thing because the probability that z is equal to 2 is it's not a standard notation, but it's infinitely small, right? Questions here on this notation? So again, the standard normal distribution, right, is we're trying to find the area underneath this curve, right? So, right, we know that for this, right, just like I said, the fact that that equation I gave earlier, the one with the e and the square and the square root of pi, that just gives you the height of the curve. So that gives you the probability density function, the value, the exact outputs of it, which aren't that helpful, right? Because any value has a basically an infinitely small chance, right? If there were an easy equation that could give me the area, say, between 0 and 1, that would be great. But there isn't, right? So we have to use approximations. And that's what this table is going to come in to help us with, right? Before we get into that, I will probably take a break. But first off, any questions on what's been presented so far? Okay, so let's take a break for 5 minutes, so until 2:45. But if you can, right, why don't you, with that, talk to your partner, maybe just kind of look at this table. I'm going to ask some questions. I'm going to ask you guys for observations, right? So maybe you can think of it in the format as, what do you notice? What do you wonder, right, when you look at this table? Do you kind of see what I'm saying? All right, so let's take a break. Use the All right, so let's come back together. And I'm not looking for anything groundbreaking, right? I wouldn't expect it because you're just looking at it. What's something that, so I have the table here, right? This is one side. This is the other side. Anyone notice anything about the table? Or this isn't quite all of the table, but much of it. Anyone notice anything? About the table? I'm not looking for anything groundbreaking, just anything. Yeah, Ulysses. Okay, so it goes up to 1, right? And on this side, right, the side that has the positive z numbers, right, the further down you are, the larger these numbers go, but they get really close to 1, but they never get to 1. Why do we think that they never get to 1? It's okay. Any thought? Yeah, you have an answer? It's okay if anyone does. What do you think? So what do we say for a continuous distribution? The total area underneath the curve is always, so it shouldn't be more than 1, right? Because these numbers in the probability, in the curve, in this table correspond to probabilities. Now on this side, so you notice that's the largest value and they increase as we get down there, right? On this side with positive z values, what is the smallest value on this side of the table? Anyone notice that? Half. That makes sense because the normal distribution is a symmetric distribution, right? So a z-score of 0 means no standard deviations, right? It means that you're at the mean. So that should be halfway between the two extremes, right? So exactly half of the area is on the z side, is on this side of the table, right? The other half of the area is on this side of the table, right? The negative side. All right, so let's teach you how to read this table, right? And what does it mean, okay? We'll also teach you how to do it in the calculator, right? So this table is only for a standard normal distribution, but we'll learn how to use it on Wednesday for non-standard distributions, right? Mean is 0, standard deviation of 1, right? So this is called table A2, right? So in your textbook, this is table A2. A lot of the homework problems I will assign, I think you might even have a link directly to a digital version of this table. There's a digital version of this table on my Canvas page. It's also in the appendix of your online textbook, which hopefully you guys spend at least some time reading, looking at, right? So what this table does, read what it says. The top of this table says table values represent area to the left of the z-score, right? So that's exactly how you read it. So you use the front side for negative z-scores, back side for positive z-scores. I'm not sure I hole punched all of them correctly, so you have to figure out which is the front and the back side, right? So what it does, right, is for a corresponding value of z, it tells you what this area is over here, right? So I will have something that you can draw on each of these. So let's start here, right? So let's draw, and maybe you guys can do this to help you remember how to use these. Draw a normal curve. It should look better than mine, right? The normal curve is always centered at, the standard normal curve is centered at 0, right? Which is why notice that 0 corresponds to 0.5, right? Let's how to choose this, right? So let's say my favorite number is 6.1, right? Negative 6.1. Notice all of these numbers, right, are negative. So I didn't draw perfectly, right? But this is z, right? So if that number right here, right, if this number were 2 point, this is what I want you to draw on your table. This is just a random example I'm drawing right now. This is how you read it, right? So to the left of negative 6.01, this area right here is roughly 2.0, roughly 27%, right? So roughly 27% of your area is to the left of negative 6.1, right? And that's why all of the z-score, that's why all of the numbers in the table on this side are less than a half. Because we're all looking about area that is to left of some vertical line that is left of center, right? Does that make sense why these numbers are less than 1/2? On this side, you read it the same way. It's just numbers that are on the other side, right? So here you're always finding the area that's to the right of some positive z value. So I showed you it in a picture form. Here, let me just show you it in an equation form. So let's choose this value right here. Hopefully you guys have three tables. This is a z-value of 0.603, right? We see that? So that means the probability that z is less than 0.603 is equal to 0.73565. Or another way you can say this, that's a probability, or if this is discrete, like if this is every person in the world, right? The 73.5%, right, are below 0.63. Does everyone able kind of thinks that they can understand how to read this table? Even if you're having trouble to understand exactly what that means. That's okay. So we will go through that, right? So let's do an example problem, right? So so people have different densities of their bones, right? If your bones have a low mineral density, they can break easily. That's not good, right? So, right, if you use some tests that just bone density people know about, right? Doctors, right? They tell you, Muna goes in and gets her value. She doesn't know what the hell that means if she's not an expert in this, right? But if they give you a z-score, we all know what that means, right? If you understand basic statistics without knowing much about the subject, right? So let's just say that they do that, right? So let's say, so again, right, we know this is a standard normal, right? So mean of 0, standard deviation of 1, we can use this table, right? So we're trying to figure out the probability that a person has a bone density test score of less than 1.27, right? First off, before we even try using this table, is this going to be a number that is less than half or more than half? Well, let's draw out a picture because we like to draw a picture every time we do this. So 1.27, is that going to be in left of center or right of center, everybody? Right of center. And we are looking at the area to the right of this vertical line or to the left of it? Left. So this area should be more than a half, right? It's our sanity check, right? So we go to our table. We look for what it was. I think it was 1.27. Wrong side of the table. So 1.2, this is 0.7. So that's the number that I am going to use. So I just found out that this probability is equal to this number, which is roughly 90%. So if you have this bone density score, roughly 90, you're roughly, I don't know what's better. I guess that's better, right? If you have denser bones than 9 out of 10 people, right? That's your percentile score. That's how you read this, right? Is everyone kind of starting to see how we use this table? So anything that is on a standard normal distribution, we can use this. Yeah, question. No particular reason, but remember, right? So if you look at the table, Scott, well, first question is it's got to stop somewhere, right? Because in a continuous distribution, right? I mean, there's like the zero problem if we're talking about human height or something, but imagine that that's not really an issue, right? There's some non-zero probability you're anywhere away from the normal curve, 300 standard deviations, right? But we learned before, and this is true, right? We see this here. We said anything that's more than 2 standard deviations, right, away, that's like 5% chance. You can actually see that because those numbers are roughly half of 5% there, right? So that's dividing the 2.5%, right? Now, at 4, right, notice how small those numbers are. 0.00, there's 4 zeros and then a 3, right? So that's like 3,000ths of 1%, right? So the idea is if you're more than 4 standard deviations away, that's in a 1 in 10,000, right? Like this is a once in a lifetime. This is like this is Armageddon, right? The meteor striking the Earth. So the probabilities there are so low that we consider that we don't really need them. If you really needed those for some obscure reason, you would use some sort of technology that can get you them there anyways. So hopefully that kind of answers that. All right. So a person is considered normal, right, if their bone density is above -1, right? Maybe you have an abnormally high, but that's not a big deal, right? What you're really worried about is having bone density too low, right? You trip on some stupid toy that maybe a younger sibling left outside, right? You fall over, you break all your bones if you're under -1, right? We don't, not good. So not quite all of your bones, but you're at higher risk, right? These are like older people, mostly older women, right? That might fall, right? Break a hip, break a bone if they just fall, right? So let's look at this. So in this case, it's a little bit different. So one, right? Is this sentence, right? Something, one part of it, what you have to do is translate the English sentence to a statement about a z-score. Is this the statement that the sentence is translating to, or am I incorrect here? Read it carefully. No, what did I do wrong? Yeah, right. It says above -1, right? Sometimes you got to be careful with some English sentences. Like you might say at least. Least sounds like less, but it's not, right? But you're definitely right. We're talking about more than 1, right? So let's draw this out. So -1, is that left or right of center? Okay, so that's my -1. And now we want the area that's to the left of this or to the right of this now? To the right, because it says more than, right? So I'm looking for a value that's more than a half, right? But here's the somewhat problematic. This makes this a little bit trickier. This table, it says something that we don't like. This table says what? This gives us areas to the left, right? But what's the total area underneath the curve? 1, right? So we can kind of use that to help us out, right? So our table, when we finally look at our table, it will actually give us this green area. But we know that if I subtract the green area from 1, I should get the yellow area, right? So when you have something that is greater than, you want to do 1 minus, flip the sign to less than, right? Now, you can I do this exact? Remember with the discrete probability distribution, right? When I was talking about using the binomial CDF on your calculator, there's something like this, but you have to be more cautious, right? Because right? I said 3 or fewer, the opposite of that would be like 3 or more, the opposite of that would be 2 or fewer, right? The one thing that's nice about a discrete, that's nice about a continuous is that the probability you choose exactly any value is infinitely small, so we don't have to worry about that, right? But in discrete, you cannot use this formula, right? Because you would have to figure out what's the probability that z is exactly equal to -1. Understand the difference, right? So then we can use this. So I'm going to tell you this. You guys practice looking this up in your table. So find the green area by looking at your table. I'll write it down once you think you have it. Point out the correct value to the person sitting next to you on the table. Did anyone get the value they find on their table to be 1.158666? Okay, so then that means that the probability is 0.84134, or roughly approximately 84%. So notice sometimes we have to be more sophisticated, right? Our table is only able to give us left area, so we actually found this white area, and since we knew that the whole area was 1, we were able to subtract to find it, right? So notice so far we've been looking at areas that are divided by a single vertical line, right? I tell you where this vertical line is, right? You can tell me what's the probability I'm to the left of it or the right of it, aka how much area is to the left of it, the vertical line, or to the right of the vertical line. And it's easy because if you know one of those answers, you know the other one, because the two answers to those two questions I gave always add up to 1, right? Now the other question might be, what if I have 2 vertical lines? What's the area between those two, right? So that's what we're going to kind of look at in the next question. So, right, I guess this is bad, right? To have low bone density. This is called osteopenia. I guess if you're below -2.5, that might be more severe than like a regular case, and that must have some other name. If that's your case, maybe, if someone touches you too hard, you just break it to a million pieces. I don't know. Not a doctor. Okay. So let's see how we can write this out. So here we're looking for the probability. So when I see between, right, notice I'm going to have z looking something like this. So I know that z is more than 2.5, but is less than, what's it less than? -1, right? Not 1. So if I'm drawing my picture, right, that does not look like a bell at all. Oh boy, wow, that is crappy. It's all right. Okay, so both of my vertical lines in this case are, where are they? They're both left of center, right? So I'm trying to find this green area. Any thoughts on how I might do that with this table, considering this table only puts one vertical line there? Well, any thoughts? Any thoughts? I heard some ideas, some from this side of the room. Any thoughts on what I might do? Yeah, Ulysses.
You can find the value of negative 2.5, and then you find the value of negative 1, and you just, what we did with the other one, like find the right of it, you find the value of that, and then the value of negative 2.5, add it together, and subtract it from 1.
Yeah, that actually does work, right? There's a slightly, right, but basically you use something with the value of 2.5 and the value from 1, right? Now, maybe this is what you're saying, right? But we can actually do this, right? Since our table only finds values of the left, we can do something that's almost exactly what Ulysses said, but just a tiny bit easier, right? So notice I can take the value, even though that where z is less than 1, right? Let's highlight that in the table in yellow. Might overgo the green, right? But so this is to the left of 1, negative 1, right? From that, left area, if I find the area that's to the left, this is the only part that's a little bit different. Instead of the right, we're finding the area that's from the left of it. I think your thing would have ended up finding it, the correct answer, Ulysses, but it would have taken maybe 1 or 2 extra steps, right? But no, really good thinking, right? I really like the thinking. It's just same. Should be using the highlighter. Same idea, just a little bit different, right? If I subtract this blue area, which is now, does everyone see that that will give me what used to be the green area, right? We able to see that, right? So I'm taking the area to the left of the line on the right minus the area left of the line on the left. That's going to be the thing that's going to be remaining is the area between the two. So we go to our table, we look up negative 1. Or sorry, positive, yeah, negative 1. That gets us 1.5866. And then from that, we subtract I hope no one's struggling at reading the table at this point, right? We all pretty good at that. Maybe we don't always know what to do with it, right? You subtract it. Right, and notice negative 2.5 is an exceptionally low value, which is why we have a very small area to the left of it, right? Which kind of goes to Ulysses' questions earlier. Why do we only need 4? Well, when we're at 4, we're really looking at things that are thousands of thousands, right? So this is approximately 15.2% of people have their bone density in this area. Another way of saying that is the probability of if I randomly select a person off the street, right, the probability that their bone density would be that low is 15.2%, right? This to show you, this is the 2 areas that we subtract, right? Now your calculator can do this yourself, right? If you don't like using the table. But again, if I just gave this to you, you would not have a really good intuition of what the hell's going on, right? So let's show you how to do this. So remember before, right, we find our binomial distributions in the distribution menu. Same thing, so continuous and discrete distributions are both found in the distribution menu. So you hit second, vars. And now notice normal distribution, since it's the most common one, it's the most important one in statistics, it's right up top. Before we had the binomial PDF, before we used binomial PDF and CDF, depending on our scenario. The nice thing is in this class, you will never use the PDF because the PDF just gives me the height of the curve at that, right? We're always interested in the area, right? So never use option 1. I'm sorry it's the first one there, but never use it, okay? So you type your left bound. And your right bound, and notice this gave us the same answer that we just found with our table, right? I'm okay if you use your calculator every single time or you use the table every single time. Why then did I spend so much time on teaching you how to use the table? Well, like it strengthens your conceptual understanding of what we're doing, right? You're going to forget if I just showed you how to use the calculator right away, probably not going to have that good of an understanding. Now, just like that with some tricks, right? Just like you have to use some tricks to get value because the table only finds area to the left. Your calculator only finds the area between two vertical lines, right? So let's say I wanted to find, if I wanted to use my calculator, right? Let's say I want to use my calculator to find that z is less than 2.1. Now I can easily do this with my table, but with the calculator, I need to give two values, right? But here I only have one. So this kind of comes to the idea that Ulysses was asking us about. Why does the value stop at -4? Because there's not much area to the left of -4. So this area right here would be roughly the same area. Let's just choose a large negative number, right? Isaac, what's a favorite number of yours? What? Large number? -190, right? This is the same. This is the same thing. I can use a number, pretty much any number larger than -10 would work here, right? This is going to be roughly the same thing. So I could type in normal CDF -190 to 2.1, right? Because there's no, right? It's subtract, sure, this thing is subtracting that area to the left of -190, but that is like, it's like finding a person that is 2 inches tall type of stuff, right? That ain't happening, right? Likewise, if I wanted to find the probability that X was greater than 1 point, well, I could subtract it, but if I wanted to calculate that directly from my calculator, that you could say that's roughly the same probability that X is between 2.1 and, I don't know, Frank, let's choose your fun large number for you.
300?
Sure. You could have gone with 30 or even 13, right? Just whatever. If you don't like this flexibility, just use 99, okay, class, right? You can try using different large numbers. You'll see that it matters very little if I put in 300, 3000, or 30, or 13. If it's more than 4, it's way out of what's on this table, right? It might change some of these long places after, right? Like the 5th, 6th decimal place. You use these numbers, it's not going to change it at all. Do we understand how to use this trick if you want to use your calculator? Also, you don't need to know this trick because you can just use the table if you want, right? Questions so far? Okay. So my next slide is titled Doing the Opposite. So let's think about this, what I mean by that. Before you do that, right? So don't write this down yet. Just think about what I'm saying here. So far, I give you a z-score, right? You find a probability / an area, right? That's what we've been doing so far, right? I tell you a z-score is z-scores, right? let's just think of the one case. I give you a z-score, right? I'm telling you, here's your curve. Put your vertical line here. When I put my vertical line here, how does that cut up the area, right? How much area is to the left or how much area is to the right? I could also ask a different question. I could say, I want 70% of my area to be to the left, or in this case, 75. So I could say, here's my curve. I want to place my line so I have 75 to the left and 25 to the right. Right? So we also need to figure out what this slide is doing, right? It's teaching us how to do this. Right? How do I go from an area, right, to a z-score? So I have my curve. I'm telling you, this is how I want it split up, right? Where do I place my vertical line? That's a totally different question, right? But a similar one. But you got to be able to notice what you're asking, right? So that is kind of the inverse process. And they use a number that specifies this, right? So the notation is with a subscript of alpha or some number, right? So right, if I write z alpha 0.25 equals, I'm asking you what z value has 25% of the area to the right. Unfortunately, that's kind of sucks because everything, technology, the table, it's designed for finding area to the left. But you can fix that by just doing 1 minus, right? So that's what you do, right? Hopefully, I'm going to try not to use that notation much because it's confusing. I'm going to try to ask the question in words so you know whether I'm thinking left or right and you don't have to remember, right? So you can think of it as a question that you know the answer, right? Kind of like Jeopardy. So I'm trying to find, I want my answer to be, well, for the left part, 75%, or the probability to be 0.75. So I'm saying z is less than z less than some number, right? That's going to equal 0.75, right? My question then is, what is that number? We know one thing, is z going to be positive or negative here, class? It's going to be, so 75% of the area is to the left, so that line should be left or right of center. Does everyone see that it's right? 75% of the area is to the left. So I'm going to be looking for a line that's right of center, right? Also notice we're going to be finding 75 in the body of the table, right? So we're right of center, so let's make sure you're on the right side of your table here. So this is the correct side of your table, right? So notice on this table, right, the values on the perimeter of the table on the left and on the top correspond to z values, right? What we are looking for right now, we don't have a z value. We have an area or a probability. Probabilities and areas are in the body of the table, right? This is our first process. Before we would start at the perimeter and go to the body of the table, right? Here, we are going to do the opposite, right? So remember, the question that we are asking ourselves here is, I know this area, in this case, is 75% or 0.75. The Z, I want to know what it equals, right? So I want to find out this question mark here, right? So to do that, I want to find the number 0.75 in the body of the table, all right? Now, the fact that these numbers are ordered makes that easier, right? So, and you're typically, since we're using it backwards, you won't typically find the exact value. But I see two values that are very close to 0.75. That's this one and this one, right? So if I had a value, if it was on there, it'd be somewhere between those, where that O is, right? So I don't know the exact Z-score, but I know it's somewhere in the 0.6 range. And specifically, I know it's between the 7 and the 8, right? So I go 7.5. So I would say Z equals 0.675, since it's between the two. Now, it's not perfectly between the two, so you could say maybe I should interpolate a little bit more. Which side is it closer to? I don't know. I don't need it that precise, right? So, where's I here? So the question mark is equal to whatever we just found. So AKA Z 0.25. 2.5 is to the right when Z is equal to 0.65. So we discovered this fact here. Questions on how I did this? All right, this is complicated, right? This is different, right? So here's why I want you to talk to the people around you, right? To have a discussion to make sure that you understand what's going on here. How is this question different than the questions I asked in the previous slides, right? And what am I meaning by inverse processes, right? Like, how is this the opposite of the previous one, right? Like, when do you do what we did, look for a number in the body of the table, and when do you find a number on the edge of the table and look for the corresponding number in the bottom, right? Do you guys understand what I'm talking about? So basically, I'm looking at what are the differences between the two? How do you know which process to do? Everyone's following what my question is, even if they don't know the answer for it? Okay, so let's talk about it. This should help strengthen your idea. So talk about it with your partner or in a small group. Okay, any questions here? Are we kind of getting the differences? The way I think about it, I never didn't think about it exactly this way until here. I have this set, right? Standardized curve. I gave you a very complicated equation that you probably didn't like too much with the e's and the square root of 2 pi, all this crazy stuff, right? That looks like it's like math you don't want to have anything to do with. But we have this table that tells you it, right? So I have this set curve before, right? I was putting in two vertical lines, but in the one vertical line problems, I was saying, if I put a vertical line here, how does that split up the area, right? How much area is to the left? How much is to the right? So I say, hey, if I put in vertical line at Z equals 1.25, what percentage is to the left? What percentage is to the right? Right here, I'm saying I want that vertical line, so it splits it up 75-25 or 30-70, right? Or 15.2 84.8, right? That's the difference, right? Here I'm asking, where do I put the line if I want to split up a certain way? Before I'm saying the line is here. How is it split up? That's the difference, right? You kind of following? Right? So since this is a different question, right? There's a different way to do this with technology, but again, I just wanted to caution you. that if I'm going to try to avoid this, right? But if you are asked to find z of, say, 0.1, this 0.1 is the area to the right. So you really want to change this to, so z of this, right, means look for 1 minus 0.1, 0.9 in the table, okay? I'm going to try not, like I promise on the celebration, I'm not just going to ask you to look for z something, right? I will write it in words, something like find the line, find the z-score such that the probability going over it is 10% or something like that, right? So just remember that, right? Why we use this notation, I don't know, but that's just the notation. Yes, it doesn't, because it's easy enough because these numbers on here are pretty, right? Like if you look at this table, 13%, sure, let's do it. So 13% to the, let's say it's to the, we're talking to the left just for sake of simplicity, right? That's going to be something on this side of the table since it's less than 2.5. Be about, so that would give us z, something between those two. Z is negative 2.25, right? So it's not any easier if it's a factor of 5 or if it's 13 or whatever, right? That makes sense? Okay, so also technology is there. Again, though, if I just went, students get confused by the name of this stuff, right? So I just want to show what you can use technology for. So if I said I want you to find, so technology uses the left and you use the inverse normal, right? So if I say I want you to find out, there's some z-score that gives us a probability, right? Of 0.6, right? What is this z-score? Right? That's the question I'm trying to find out right now. The way to do this, right, is to, on your calculator, right? The way to do this in your table would be to hunt for the number that's closest to 60%, right? 0.6. Oh. Yeah, and the reason why, I use those sort of examples in class is that they're easier to say out loud, and then it's easier to remember 15%, conceptualize it, than 13.2%, right? So it's just easier to say it when we're communicating with each other. But it's not any more difficult to solve when you're not speaking, when you're looking at a piece of paper. So same thing. If I hit second vars, I go to my distributions, right? So remember, never use the normal PDF there. It's a trap, right? This is our normal CDF. Notice the thing under it, it says IVN norm. Norm, we can guess, stands for, and IVN stands for inverse. So it's saying, take a probability, give me the z-score that cuts that much probability to the left of that z-score, right? So we go to invert norm. For invert norm, you just put in a single number because we're looking to the left. I type in 0.6. Before I hit enter, am I going to get a number that is positive or negative? So I want 60% of my area to be to the left of this mysterious z-score. So this mysterious z-score, is that going to be a positive number or a negative one? Positive, because it's to the left of the center, right? So, and indeed, it in fact is positive. It's about 2.5. So we typed that in, we got out 0.5, so that means that question mark is 0.5, aka the probability that z is less than 0.25 is 0.6.